So today we'll start with module 3, right? Module 2 we had dealt with generation of high voltages, okay, and currents. Also we had seen HVDC, HVDC generation, HVDC voltages, HVDC currents, generation of impulses we had seen. So whatever we had seen the generation, now we want an instrument to measure the generated high voltage. So those instruments to measure, how do we measure the high voltages? We'll see it in module 3. Module 3 hence deals with measurement of high direct current voltages, measurement of high AC and impulse voltages, measurement of high currents, let it be DC or AC, and also the impulse currents, the CROs, cathode ray oscilloscopes, which we are using for the measurement of impulse voltage and currents. Okay, these things we'll see in our module 3. Now, talking about the techniques for high voltage measurement. So there are different techniques. Okay, now the method or the technique used to measure HVDC include series resistance micrometer, then use of potential divider, use of generating voltmeters. We can use sphere and other spark gaps in order to measure the HVDC voltages. Okay. Now, the HVAC with power frequency 50 Hz, we can measure using series impedance emitters, potential dividers. Let it be, we can use resistance potential divider or capacitance potential divider. We can go for potential transformers, okay, electromagnetic or CVT type. Then we can use electrostatic voltmeters and again the sphere gap for measuring HVAC with power frequency. Similarly, HVAC with high frequency voltages and the impulse voltages, okay, and other rapidly changing voltages, we can measure using any of these methods, which include potential dividers, capacitive dividers, peak voltmeters or sphere gaps. Okay. Then to measure the direct currents, we can use resistive shunts with milliammeter. We can go for the Hall effect generators or the magnetic links, right? Similarly, AC with power frequency and high frequency AC currents. Okay, last slide I had told you AC voltage measurement. This is current. See, high current measuring techniques. This was high voltage measuring techniques. So here we'll study all these methods or the techniques. Okay, so these all methods we are going to study in our module 3. So starting with first one, the series resistance micrometer. DC voltages are usually measured by connecting a very high resistance, okay, of few hundred of mega ohms in series with resistance, okay, in series with a micrometer, okay, in series with a micrometer. Okay, so what I have shown you here, to measure high voltage DC, we connect very high resistance of ohms of range mega ohms in series with the micrometer, which is shown here. Okay, so only the current I flowing through the large calibrated resistance R is measured by the moving coil emitter. So this is my moving coil emitter. Okay, so in this case the voltage of the source is given by our Ohm's law, which is given as V is equal to IR. Okay, so here the voltage drop in the meter, okay, the micrometer meter is negligible, okay, as the impedance of the meter is only a few ohms compared to few hundred mega ohms of the series resistance are. Okay, so here if you see, we have connected a mega ohm resistance in series with micro emitter. Okay, so here it is said that since this meter is having the resistance of range micro, okay, so voltage drop in this meter is neglected. Okay, because here it is mega ohm, so compared to mega ohms, microamperes is negligible. Okay, now here a protective device, like, okay, you can see here a protective device. Okay, this is my protective device. So a protective device, we can use a paper gap, okay, a neon glow tube or a Zener diode with suitable series resistance is connected across the meter as a protection against high voltages in case series resistance R fails or flashes over. It means, right, it means in case if this resistance fails, the high current should not pass through the micro emitter. If it does so, my measuring kit will be damaged. So as to protect that measuring device, we are connecting one more protective device in parallel or across that micro emitter. Okay, so if we put this gap, it means all the current which is coming from here will flow through this gap in case the resistance fails. Okay, now the ohmic value of series resistance R is chosen such that a current of 1 to 10 microampere is allowed for full scale deflection of that micro emitter. Okay, the resistance is constructed, the construction of resistor I am talking, the high resistance of mega ohms. The resistance is constructed from a large number of wire wound resistors in series. Okay, so the voltage drop in each resistor element is chosen to avoid surface flashovers and discharges, right? So when we are talking about this, a value of say less than 5 kilovolt per centimeter, okay, 5 kilovolt per centimeter when we talk in air, or it can be less than 20 kilovolt per centimeter when I am talking in good oil. Okay, that is permissible. Okay, so a resistor chain I was talking is provided with corona free terminations. Okay, resistance chain, because here I said we have resistors connected in series, so that resistor chain is provided with corona free terminations, right? Here this series resistance micro emitter is having some limitations. Okay, so first limitation with this is power dissipation and the source loading. Okay, here the power dissipation is more and the source loading effect can be seen. Next is the effect of temperature and long time stability. Okay, then voltage dependence of resistive elements and sensitivity to mechanical stresses are seen. So this series resistance micro emitters which we are talking, okay, these are built for the ranges of 500 kilovolt DC. Okay, so these are designed for the ranges of 500 kilovolt DC. Okay, and the accuracy is it's better than 0.2%. Okay, so I hope this was understood. The diagram of this is shown here. Okay, you can see. Okay, this is the diagram of series resistance micro emitter. It depends on the basic principle that, see, when you give the high voltage, the current will flow through this. This current has to flow through a resistance of the range of mega ohms. So this resistance is so chosen that only how much I told you, up till 10, okay, 1 to 10 microampere of current is allowed to flow through this resistance, such that it passes through this micrometer and it gets measured. In case this resistance fails, the current, instead of flowing through this, it sees this direction, okay, through the protective device, in order to save my device from getting damaged. Okay, so this is all about series resistance micrometer. So next technique to measure high voltage DC voltages is the resistance potential divider circuit. So this resistance potential divider circuit can be implemented using a electrostatic or a high impedance voltmeter. The influence of temperature and the voltage on the elements is thus eliminated in the voltage divider arrangement. Okay, so this is the circuit where you can see this is the voltage divider arrangement. The high voltage magnitude is given by V2 into R1 plus R2 by R2. Okay, where V2 is the DC voltage across the low voltage arm, R2. Okay, so with sudden changes in the voltage, such as switching operations, flashover of test objects, or source short circuits, flashover or damage may occur to the ground capacitances. Okay, so to avoid these transient voltages, voltage controlling capacitors are connected across the elements. Okay, also a corona free termination is also necessary to avoid unnecessary discharges at high voltage ends. Okay, so a series resistance micrometer with a parallel capacitor connection for linearization of transient potential distribution is provided. Okay, the potential dividers, this type of potential dividers are made with the accuracy of 0.05% for up to voltages of 100 kilovolt, 0.1% for up to voltages of 300 kilovolt, and 0.5% accuracy for 500 kilovolts. Okay, so this is all about a potential divider circuit. To measure HVDC is using generating voltmeter principle. Okay, so we'll see the generating voltmeters principle and construction. Okay, high voltage measuring devices employ generating principle when source loading is prohibited. Okay, as in the case of Van de Graaff generators we had seen, or when direct connection to high voltage source is to be avoided. Okay, so a generating voltmeter, a generating voltmeter is a variable capacitor electrostatic voltage generator which generates current proportional to the applied external voltage. Okay, so the device here, the generating voltmeter device, is driven by an external synchronous or constant speed motor, and this does not absorb power or energy from the voltage measuring sources. Okay, so this is about generating voltmeter. Okay, now we'll see the principle of operation. Okay, now the charge stored in the capacitor of capacitance C is given by, we all know, Q is equal to CV or C is equal to Q by V. Okay, now if the capacitance of the capacitor varies with the time, okay, varies with the time when connected to the source of voltage V, the current through the capacitor I becomes what? dq by I becomes dq by dt or V into dc by dt plus c dv by dt. So this is the current through the total current through the capacitor. Okay. However, if we see, we are talking about DC voltage now. So for DC voltages, we know dv by dt is equal to 0. So this part tends to going to 0. Hence my I is dq by dt, which is equal to V dc by dt. Okay. Now the capacitance which we are talking, okay, if the capacitance C varies between the limits C0 and C0 plus Cm, okay, sinusoidally, okay, then total capacitance C is given as C is equal to C0 plus Cm into sin omega t, okay, and the current value is given as I is equal to Im cos omega t, or if I replace, I get, or if I substitute I for the value of I get Im equals to V into Cm into omega. Okay. Now this is the final value or the average value. The RMS value of current can be given as IRMS equal to VCm omega by root 2. Okay. So this is the principle of operation of generating voltmeters. Right. Now from where does this capacitance come into picture? We'll see here in the construction. Okay. Now here see a generating voltmeter principle and construction with a rotating cylinder. Okay, with a rotating cylinder consists of two exciting field electrodes. Okay, you can see this. Okay, I'll tell you here. It consists of two exciting field electrodes and a rotating two-pole armature driven by a synchronous motor at a constant speed n. So you can see here, it consists of a rotating cylinder. Okay, you see, this is it is something like a cylinder. Okay, consists of two exciting field electrodes. Okay, there are two electrodes onto which excitation is provided, and there are two rotating pole armature which are driven by a synchronous motor. Okay, so this motor is rotating at constant speed n. Now the AC current flowing between the two halves of the armature is rectified by a commutator, as we know, whose arithmetic mean may be calculated from I is equal to n by 30 into delta C into V, where delta C is C max minus C minimum. Okay. Now for the symmetric voltage, C minimum equal to 0. Now when the voltage is not symmetrical, one of the electrode is grounded and C minimum has a finite value. Okay, thus this C minimum will have some finite value. Okay, and the factor of proportionality, right, delta C can be is determined using done by calibration. Okay, so you can see this figure, right? Explanation, I will go to the next slide. The high voltage source is connected to a disc electrode S3. Okay, you can see here S3 is a high voltage electrode. So the high voltage source is connected to a disc electrode S3. So this is kept at a distance or at a fixed distance on the axis of other low voltage electrodes. Low voltage electrodes are S0, S1 and S2. See, no doubt S0 is rotor, but it is also acting as a electrode. Okay. So as I said, it is kept at a fixed distance on the axis of other low voltage electrodes S0, S1 and S2. Okay. So the rotor S0, I said you here, you can see S0 is the rotor. So S0 is driven at a constant speed by a synchronous motor by a suitable speed. Okay, at a constant speed of n, the rotor S0 is driven with the help of this motor. Right now, the rotor vanes of S0 cause periodic changes in the capacitance between the insulated disc S2 and the high voltage electrode S3. Okay, we will go back here. Now you can see here, okay, this is the construction of generating voltmeter. So you can see here where the capacitance comes into existence. Okay, capacitance means I have two parallel plates or the two electrodes, and in between I have the dielectric medium. Okay, so here the rotor vanes of S0. Okay, this is my S0 on which is placed. See, S0 is placed at a distance at a suitable distance from S1, S2 and S3. Okay, so the rotor vanes of S0, when it is rotating, because of this motor being rotated, okay, it causes periodic change in the capacitance. See, you can see here there is a gap between S0 and S3. Okay, so S0 and S3 are your electrodes, and the air which is the air in the gap between S0 and S3 is acting as a dielectric medium. So when we rotate S0 at some constant speed, there is a change in the capacitance between the insulated disc, okay, S2 and the high voltage electrode S2 and S3. Okay, so the shape, right, I hope up till here it is clear. Okay, now the shape and the number of vanes of S0 and S1 are so designed that they produce a sinusoidal variation in the capacitance. Right, the generated AC current, the current whichever is generated, right, the generated AC current through the resistance R is rectified and read by a moving coil instrument. Okay, so here is my moving coil instrument, which is my micrometer. So this micrometer reads the generated AC current through the resistance R, which is rectified. Okay, so that is why we are using it for DC measurement. Okay, so then an amplifier is needed. Okay, an amplifier is needed if the shunt capacitance is large or longer leads are used for connection to rectifier and the meter. Okay, so there are some disadvantages associated with this, and some of the advantages associated with the generating voltmeters. So we'll go through the advantages and disadvantages. So first thing is, here no source loading, okay, by the micrometer which we have connected. Next is, since here there is no direct connection to high voltage electrode, the possibility of the meter getting damaged is less. Next, the scale is linear and the extension of range is easier in this method, and a very convenient instrument for electrostatic devices such as Van de Graaff generator and particle accelerators. Okay, now talking about the disadvantages of generating voltmeters. First thing is, they require calibration. Every time you have to calibrate it. Okay, and careful construction is required, and is a it's cumbersome or it is difficult instrument requiring an auxiliary drive, right, which is an auxiliary drive, the motor which we are using. Okay, so there are some limitations, right, as I have mentioned here, right. Apart from this, you can also add up the disturbance, when it is rotating here, okay, when my motor is rotating, there is possibility of disturbance in the position, okay, and again mounting of the electrodes, right? So whatever calibration we have done, that becomes invalid, and again you have to redo the calibration. That is also the one more disadvantage we can add up to the generating voltmeters. Okay, so these three methods, one is your series resistance micrometer, one is resistance potential divider, and the third one is generating voltmeters. Okay, these three methods are used for the measurement of DC voltages. Okay, the fourth method which I had told you is by use of spear gaps or some other spark gaps. Okay, so this method is also there, right? But this method is used for measurement of DC voltages, also measurement of AC voltages with power frequencies, and AC voltages and impulses also. Here also you can see, okay, and here also you can see. So we'll discuss it at once, okay, but for the time being we have discussed these three methods: series resistance micrometer, resistance potential divider, and the generating voltmeters.